Hey folks, Mr. Bullock here, and I hope your studies are going well, and these videos are helping you get ready for your upcoming AP test. And good luck, by the way. All right, let's go ahead and get started. Given that 49.0% of the U.S. population are male and 12.1% of the population are over 65 years in age, can we conclude that when we multiply those, that's the percentage of population of men that are older than 65? Okay. Well, the multiplication rule says that I can do this right here if they're independent of each other. So I would say yes if they were independent of each other, or I'm going to say no, they're not, because they're not independent of each other. And I'm going to tell you that they're not independent of each other because in general, you guys, men in general do not live as long as women. So the percent of people that are over 65 tend to be more women than men right there, so they're not dependent of each other, so I get choice D. Okay, so which of the following are true statements about blocking? Blocking is to experimental design as stratification is to sampling design. Well, that's true. I'll explain that in just a second. So by controlling certain variables, blocking can make conclusions more specific. Well, that's true. And then the paired comparison design is a special case of blocking. Well, blocking in experimental design first divides the subject into representative groups. They're called blocks. So just as stratification and sampling design divides the population into representative groups called strata. So that's choice 1 is true. And this procedure can control certain variables by bringing them directly into the picture. So the conclusions are more specific. So it makes number 2 true, and the paired comparison design is a special case of blocking in which each pair can be considered a block. So all of those are true, and that's choice D. Okay, all right, so for pairs of data used to determine a regression line, y equals -2 plus 6x. If the four values of the independent variable are 37, 52, 18, and 23 respectively, what is the mean of the four values of the dependent variables? Okay. Well, let's find the mean of those numbers right there. The mean of those numbers is choice A, and choice A is not the answer right there. And it's because the regression line goes through x bar comma y bar. So I have to figure out my y bar. So what I got to do is plug in this x bar, this x coordinate right here, the mean right there, and that'll give me the value of the dependent variable, which is my y bar right there. So 193. So it's choice B. Okay, they tried to trick you on that one. All right, if the quartiles 1 and 3 are 50 and 70, which of the following must be true? The median is 60. Remember a box and whisker plot, you guys? The middle part of the box, you have your, this one would be like quartile 1, over here would be quartile 3. Somewhere in there is the median. It's the vertical one for the median, but it's not necessarily in the middle, so 1 isn't true. Okay, and the mean is between 50 and 70. Well, it seems like that would be true, but it might not be if we had a big old outlier, you know, way out there that pulled the mean outside of the box. So that won't be true. And the standard deviation can be affected by an outlier also. So I get none of those could be true, you guys. So because of the outliers, big outliers right there. Okay. All right, so a TV network conducts a weekly survey to determine the proportion of viewers who watch various programs. For the coming year, they decide to double the sampling size. So the main benefit to doubling the sampling size, okay, when you double the sample size, you guys, it decreases your standard deviation, because remember this formula from standard deviation right here for proportions, you guys? So your sampling proportion standard deviation formula is this, remember that? And they'll give that to you. Don't forget, they'll give that to you. And this is, and it says proportions right here, so that tells me it's this one right here with my proportions. Look, as n gets really, really large right here, when the denominator gets big, it makes this thing get small. So this is my standard deviation formula, so it's going to make my standard deviation decrease as the sampling size gets bigger. So I get choice E on that one, okay? All right, so advantages to using surveys as opposed to experiments are surveys are generally cheaper to conduct. That's true. In general, they are. Experiments usually cost money and planning and all that time, so it's generally easier to conclude a cause and effect from surveys. Well, I don't think that's true. It is for experiments, but not for surveys, I don't think. So surveys are generally not subject to bias. Well, that's not true either. So surveys are generally cheaper and quicker to conduct than experiments. However, surveys are subject to bias, and it's difficult to conclude any kind of cause and effect from the surveys. Okay, so choice A, only one works. Company wishes to survey what people think about new product it plans to market. So they decide to randomly sample their customer database, as this includes phone numbers and addresses. So this procedure is an example of what type? Well, they're doing this out of total convenience, you guys. So this one is convenience sampling right here. So convenience samples are based on choosing individuals that are easy to reach. So a typical example that we talked about a lot in class is interviews at a shopping mall. It's really convenient because people are right there. So and that data obtained from convenience samples tend to be not representative of the entire population. So, and you know, think of yourself at a mall and you want to, and here comes this big burly guy with a big beard. Not to offend anybody if you're a big burly guy with a big beard, but chances are you'd rather ask somebody else than ask that person, or you get the idea. So they just don't represent the whole population, and in general, people at the malls have more money to spend so than people that don't go, although I don't like going to the malls, and not that I'm, never mind. Okay, which of the following are true statements? The area, sorry guys, the area under a normal curve is always equal to 1, no matter what the mean and standard deviations are. Well, if it's a normal curve, that one's true. The smaller the standard deviation of a normal curve, the higher and narrow the graph is. Well, remember a bell-shaped curve, you guys? If you had this bell-shaped curve right here, okay? And so the standard deviations are those, you know, 1 standard deviation, 2 standard deviation, 3 standard deviation to the left. And well, if they're more narrow, it's going to make it a skinnier one. So this one's true also. Normal curves with different means are centered around different numbers. Well, that one's true also. So all of those guys are true. So I get choice D. All right, a piece of clothing takes an average of 38 minutes to move through an assembly line. If the standard deviation is 4 minutes and the distribution is normal, what's the probability that a piece of clothing will take over 45 minutes? Okay, this is from chapter 2 in our book, I remember. Remember this formula? Z equals x minus the mu divided by the standard deviation. X is the number we're focusing on. It's that 45 right there. The mu is the average right here. And then divided by the standard deviation, so you get 1.75, and it says takes over. So 1.75 is over to the right, so here's 0 right here. So we look up on our Z table 1.75, and you get 0.9599, but it's 1 minus that because we want this side. We don't want this side right here. So I get 0.040. All right, and we could do this in the calculator also, you guys. But so if you go to normal CDF and you plug in 45, the number that you're focusing on, you punch in 1,000 because we want to go a big number that's to the right. We want to include all of it. So we included a big number. Probably 500 could have worked on this. So we just a big number right here, and this is the mean, this is the standard deviation, and it'll give you that right there. Normal CDF is found in your second function bars, and this will also work on the TI-83s I checked. Okay. All right. Box A has 4 $10 bills and a single $100 bill. Box B has 400 $10 bills and 100 $100 bills. Box C has 28 $1 bills. You can have all of box C or blindly pick one of the one bill out of either box A or box B. Which choice offers the greatest expected winnings? Doesn't matter to me. Sign me up. I'll take this game. Okay, the lowest I can get is 28 bucks. All right. Anyway, so here's how you get box A. There's $10, and there's 4 out of the 5 bills in there are 10 bucks. So I multiply that times 10, and there's 1 out of the 5 bills in there that are 100 bucks. So when I do that, I get 28. Similarly, I get 28 for box B. So you get 20. The chances are your expected winnings are 28 bucks in either of the boxes. All right, take care, you guys.